most of you have seen or at least heard of the movie Terminator, and if not, it has parts about robots being a threat to humanity and taking over the world or something like that. Well, since the race of AI has started with ChatGPT growing in popularity, Elon Musk doing whatever he does, and AI slowly acting more human by the day, the world is going to end sooner or later. I personally don't mind, because 1, robots are cool, and 2, robots are cool, like how can... And you know what's not cool? Breathing. Well, jokes aside, but I have been working on a little research project which does actually explore the possibility of artificial brains and learning. The title of my research project is Optimizing DDPG Pathfinding Algorithm with Quadruped Training Using a Lidar Scanner.
Hell no, man. What the man?
Alright, that might not make sense, so let me explain it simply. Here is Bob. Bob is bored. Bob is also not that smart. In the distance, Bob sees something he likes. Bob's artificial neurons activate. Bob wants to go over there and see what it is. So he does exactly that. But Bob has a problem. He doesn't know how to walk. The end. Okay, so as we saw by that amazing explanation, that we want to get Bob to the target, and to do so we need to train him and he needs to learn how to walk. In order to do this, I'll be using machine learning. What is machine learning though? Machine learning is pretty much a subsection of AI. But what is AI? AI is pretty much anything that can do a task that it is programmed for. The difference with machine learning is that instead of me programming it and telling it what to do step by step, I make it an environment and give it an end goal, which it then programs itself to achieve by learning. So when I say in my title, Optimizing DDPG Pathfinding Algorithm, I'm pretty much saying making an artificial brain using DDPG, which helps me find an optimized path for the robot. Now, I keep on saying DDPG, but what is it? So let's have a deep dive into Bob's brain. Alright, so DDPG stands for Deep Deterministic Policy Gradient. Before I get into what that means, let's explore the type of artificial brains or algorithms that can be used for machine learning. First, we can talk about evolution machine learning, or EML, which kind of works like the name. As you can see with my diagram, there are millions of Bobs and they all want to reach the green cube, so they all do random moves at the start. This first generation of Bobs are idiots, but 1 or 2 of them actually made it closer. So the ones that made it closer reproduced, and this next generation does the same thing as their parents, but their next move will be slightly different. And then the process continues until one of the Bobs makes the perfect amount of moves and makes it to the end. Like this, it's kind of like a system of survival of the fittest. Now we will move on to the algorithm I used, aka DDPG. A DDPG brain kind of works like a human baby's brain, where if they make a good action, the environment senses it and gives them a small reward. But if they don't do that, they get punished. Now, there are multiple types of brains that work like this, but the difference with DDPG is that if it does something very good, it gets a very big reward, and the rewards increase based on the kind of action it does, kind of like a gradient. The rewards scale from 0 to 1, 0 being no reward and 1 being the biggest. For the bot, this reward is pretty much just 1s and 0s that it eats up. So all of these processes are being done in Bob's head, which is all being simulated in physics and Unity, which I'm using as a medium to run this algorithm. All the information that I'm giving it is the distance from the prize, what it can control like the limbs, and it dies if it falls to the ground or be punished. Now at the start of my project back in July, my plans were to make a real-life model that can walk and work on real-life grass, dirt, and stones. But after looking at the parts I would need, I quickly found out that it would literally be cheaper to buy Boston Dynamics robot dog for $200K or something like that. So I settled with the Unity physics simulation and IRL environment scanning, which I'll now discuss. Now, me switching to a physics simulation doesn't really matter, since the brain is designed to adapt to its environment. So even if I drop this on the moon with low gravity or Jupiter with high gravity, It will adapt just like it will if I transported it to real life. The only real problems are hardware issues like motor braking or a complete short circuit. This environment kinda looks simple and flat, and we gotta give it some personality. So we're gonna need terrain, but not just any terrain. Terrain scanned by a Lidar scanner. What this pretty much does is make a 3D model of its surrounding using this thingy called a Lidar scanner and some servo motors. But how does it work together? Well, first, what the scanner thingy does is it pretty much finds the exact distance from the camera using a laser and bouncing it back from the ground. After it finds the distance, we need to plot it in a 3D graph. The method I use to find the x, y, and z coordinate is simply by using some trigonometry and putting it into the third dimension. We can call this polar coordinates. What I've done is that I have a predetermined angle at which the camera will be angled at, and then I will find the distance, which will give me kinda like a hypotenuse. With this, I can print this out, transfer them through an Arduino to Microsoft Excel, then straight to a saved file. Then I wrote a quick Python script to do the conversion method shown right here, to convert the angle, distance, and height from the camera to x, y, z in a graph. After this, we have a graph called a point cloud, and from that, we can put it through a cool package transforming thingy called matplotlib.pyplot, which will connect the dots and make it into a varied terrain. And boom! Now we made Bob's life more difficult. Now that we have all the parts, we can now start the simulation. I think it's time for his first steps. Diam. Alright, run it back. Diam. Alright, so now we let it go for the next few hours and let it train. I'm gonna add these just so you don't get bored. Alright, so it's been a few hours and it's gone through a few thousand attempts and has gotten pretty good at walking and going through the terrain. So now let's test it out in a new terrain. And now it's given up. It seems like Bob's heart of passion is no more. Or maybe it's because of overfitting. Now, what is overfitting? Well, it's pretty much when your machine learning brain is too used to the first terrain that it was training on, and has pretty much memorized every part of it. This means that all that hard work that it was learning and training for is useless. Now what do? Nothing? Well, after a few hours of trying to fix Bob thinking he was just broken, I had another idea. How about we teach Bob to walk in many different environments at once, and pretty much have it happening all simultaneously at the same time? Now, this might kill my computer, but it'll all be worth it in the end. After all that training he has done, Bob has reached the final destination, his green cube. Now, if we try this again with a new environment, it's a genius. It adapts, it knows. It's a pinnacle of human destruction. Intelligence. But on a serious note, what is the point of all this? And where can this be used anyways? Isn't there already a robot dog? Well, yes, there is already a robot dog, but that robot dog has to be programmed and told what to do step by step. For this robot dog, you just gotta tell it what to do, and it'll go and do it. Some applications of this project can include the involvement in the search and rescue missions, or to go places where humans are too weak to reach. This can also help in agriculture or even military defense. Finally, if you want to read all the juicy details and a more in-depth, less beginner-friendly version of this project, I can send you the PDF of the file while I'm still waiting for the research paper to be published online. Adroit, CrewX, SFJ. These publishers haven't gotten back to me in more than 4 weeks, so I've kind of given up hope now. At the bottom of this YouTube video, I'm planning to link the PDF and all the code that I used in this project in the description, so that you guys can go to it and visit whenever you want on YouTube, and I'll keep it public forever. Special thanks to Theodore Bine, who is a comp-sci graduate at UPenn and has helped me as a mentor through this project with all the comp-sci help I needed. I also reached out to other people with help, and most of my resources were sourced online and were completely free. Planning to continue this project in uni. Thank you for watching.